Good day, everyone, and welcome to the continuation of our topic that we started in class but were unable to finish. Remember, this course is based on Standard 1, 2, and 3, built on the information that we already did in our last course in Infant 1 and 2 in Math 2002. So this particular course is Math 2003. So let's recall that when we're looking at this today, our topic is basic number facts. We have already started this, and we're just going to complete the operations part as we already did addition and subtraction in the earlier course, and now it's multiplication, which we've done in class, and today we'll complete it with division. So let's look at the question. The farmer shared 84 mangoes equally among his 6 neighbors. How many did each get? So it's simple enough. And what we're trying to do is get to the point of showing and giving support to that very complicated algorithm for long division for some students. So this is normally how it is presented. 6 as the outside number, which is our divisor, 84 as our inside number, our dividend. And when we work it out and get our answer on top, that will be our quotient. And if there's any remainders accordingly. So what do we tell the children? 6 into 84 or 6 into 8 and so forth. Right. We should try to represent this using our base 10 blocks. And we have the first case, we're actually going to do what? We're going to share it up. So we're going to share it in such a way that we're going to make a group of 6. Now, if we recall, what we're doing is we tell the children normally 6 into 8. What it actually means is that those 8, the place value for those 8 are 10s. So can we get 6, a group of 6 from the amount of 10s we have? Well, of course we can. So we can get one group of 6. Could we get a second group of 6 with the remainder? No, we do not have enough. So all we're seeing is that we're able to get one group of 6 out of those 8. And when we realize that, then how many 10s did we use just now? We had one group of 6, which gives us 6. And now we could either write the 6, so some people write the 6 and the 0, so 60, because if we have 6 10s, that's 60. Either way, different teachers have little tweaks on the way they teach this. But the point of this is we want to show it by supporting, first presenting it as concrete in order to support that abstract algorithm. So we have 84 in all, and we just found a group of 6 10s, or 60. So what's the remainder? If we look there, we can see our remainder would mean we could just remove that, and clearly it is 24. So we could do subtraction now, where the students will be able to say 24 there, 2 10s, 8 take away 6 is 2, and 4 1s. Now, we're still trying to form groups of 6. Can we find 6 from the groups of 10s that remain? No, we don't have enough. So what we can do is remove one of those 10s or regroup it and change it into 10 units. But we don't need the 10s anymore, so we'll do the same thing with the second one. And as such, we have 10 and then 20, and for 24 units. Can we share this into groups of 6? Well, there's one group of 6. Do we have enough to make another group? Yes, we do. So let's go again. Make a second group. Can we do another group? We could do that. That's 3 groups. And then, of course, we have 4 groups. So we were able to say that how many groups of 6 can we get into 24? We were able to get 4 groups of 6. So what did we use? 4 groups of 6 gave us 24. And if we used up those 24, how much is left? 0. So there's no remainder. So that's one way of showing, using base 10 blocks, how division should be presented to students. And that way, it supports how the algorithm works. Another way, we can think of integrating the topic, recognizing that we want 84 to be shared up in 6. So we could picture that as being a rectangle whose width is 6. And we don't know how long it is, but we know we want to end up with 84 of those things to be shared. So the area is 84. So if we look at this first piece using this grid, then we know the bigger or darker lines are 10 away. So 6 tens are 60. We were able to get that. And out of that 84, it means that we were able to separate and share up 60 of those. And we got 10 groups of 6 in that 60. What else? What remains after 60 will be 24. So we can now say 6 and 612 and 618 and 624. So the width of that will be 4. Therefore, 10 and 4 is 14. So there are 3 possible ways of showing division according to the level of your class without approaching that algorithm on the left-hand side. Remember, if it is that we're looking at an approach similar to that of Brunner, talking about enactive, iconic, and symbolic, right? The standard protocol is showing it symbolically or abstractly, as on the left. But students are able to get a better grasp and build conceptual understanding if they're able to manipulate it, right? Which is the enactive way or the concrete way. And when they develop further, they can actually draw it. Let's go on. Let's do another example. 3 baskets have to be evenly filled with 306 fruits. So how many fruits are in each basket? So we have 3 into 306. We're using base 10 blocks so we could see it. 100, 200, 300, and 6 units. So we can, if we look at the squares, can we get a group of 3? We can get 1 group of 3. So 3, sometimes we make mistakes and we say 3 into 3 is 1. That's not actually correct. What it is out of the 3 squares, how many groups of 3 can we get? We can get 1 group of those. And those are hundreds. Now, do we have any 10s? We don't have any 10s. But remember, we're trying to see what is the remainder. When we are able to remove this 300 from there, then that can be represented as subtraction. And we're left with 3 take away 3 is 0, 0 take away 0 is 0. So we're left with, right? And 3 into 0, there's nothing there, no 10s to share up. So we're left with 6. And we can divide that into a group of 3 and another group of 3. So we could get 2 groups of 3s. And what we do, if we use up 2 groups of 3, we want to see when we remove that, how much remains, and that's 0. Let's show the same thing using this multigrid. 306 can be broken up into something in terms of area as 306, and we know with it, one side is 3, we need to know the other side. So if we know that is 3, we can draw a line straight across 10, 20, 30, 40, 50. So that width is 50. So 3 times 50 indicates 150. So some teachers use this method to show the students, look, we don't have to divide 306. We could try and share up 150, and that gave us 50 of those. 50 groups of 3. If we consider a column as 3, then we had 50 columns. And we can repeat that again, which will give us another 50. So that's 150 and 150. So we're able to say We got 50 and 50, 100. And what is remaining? 6 is the remainder because we want to get 306. So we can easily split that up there. And we have a length and breadth 3 times 2, or 2 groups of 3. So we have 50 and 50, 100, and 2, 102. So 3 baskets have to be evenly filled with 306 fruits. So each basket will get 102 fruits. Let's try another one. The principal got 1,242 toys to be shared equally among 9 classes. How many did each class get? So we can easily represent that with the normal algorithm, with the divisor being 9 and 1,242 being the dividend. So let's represent that with 1 cube, which shows 1,000. We have 2 squares, 4 rods, and 2 units. Of course, we can't get 9 in a group of 9 with the cubes, so we have to replace the cube or regroup it, break it up if you wish, into 10 squares. So how many squares do we have in all now? 10, 11, 12. And if you look at it, you'll see there are 12 squares or 12 hundreds. Can we form a group of 9 here? Yes, we can easily form one group of 9. So if we have one group of 9, we have one square. Can we get a second group of 9 there in the squares? No, we can't. So we have one square. So we can put that up. And what that means is out of the 12, we use 9. So how much remains? Would be 3 remains on top. So we have 342 remaining. So if you want, we're no longer looking for forming groups of 9 with the squares because we don't have enough. So we now have to form groups of 9 using the rods, using the tens. So that's why we're looking at 34 tens. And just for students to recognize that we were able to remove each square and replace it by 10 rods. And there were 3 squares, so there's 3 tens at 30, and for 34 tens. Can we form groups of 9? Well, there's one group of 9, another group of 9, a third group of 9. Do we have enough for a fourth group? Let's count it. 1, 2, 3, 4, 5, 6, 7. Not quite enough yet. So we were able to form 3 groups of 9 rods. So 3 rods or 3 tens, right? So we can put it there under that column. So we have 3 nines, and if that is what we're using, we want to find out how much is being left so that we can now share those up. And we can count it: 4, 5, 6, 7, 7 tens and 2 ones, right? So we should have 7 tens remaining. Let's deal with that first. 34 minus 27, you can do your normal regrouping and stuff, and give you 7. 7 tens, and bring down the 2. So now we have to take the 7 tens and break them up, or we group them into 72 units. And now we break those up into groups of 9, and we're able to get 8 of those. So if we got 8 groups of 9, we use 72. Are there any remaining? There's no more. So you can print these out just as I gave you the manipulatives and share these out, and the students are able to take them and regroup and understand and see exactly how the algorithm is working and how sharing is. So we have 1,242. It's the same question, right? And we're making it, we have 9 wide by 50. 9 by 50 is 450. And then we have another 450, which gives us 900. And we had 9 tens are 90. So that's 9. So the first case, we got 50 columns of 9. The second case, we got 50 columns of 9. Now we have how many columns of 9? 10 columns of 9. So that gives us 990. Let's do another 10. So that'll give us another 10 groups of 9. And then we could get another 10. So It really means an addition question here. So we had 450 and 450, 990, 1080, 1170. We're almost there. 1170. So what is missing is 72 of them. And if we have 72 here, if we count them, we have how many columns? 1, 2, 3, 4, 5, 6, 7, 8. As such, 50, how many groups of 9 do we have? 50 and 50, 100, 110, 120, 150, 138. So this is another way of showing it. Right? You're indicating groups of 9s. Let's now look at types of numbers. So hopefully this gives you a little recap in terms of how do we handle these numbers. Let's look at the first number, number 1. Number 1 is a square. It's 1 by 1, if we're thinking of length by breadth. And we can't manipulate that anyway. Let's look at number 2. Number 2, it has 1, 2 squares. And those 2 squares, can it be manipulated any way different? Remember, it's 1 by 2. Most we can do is turn it. It will still give us the dimensions of 1 and 2. Right? So we are able to say that a 1 gives us a square. The 2, if we have 2 of those, we put them next to each other, we get a rectangle, whether we have it horizontal or vertical. What about 3? So 3, 1, 2, 3. Can we rearrange this to form any other quadrilateral? Well, we can't. So its length and breadth are 1 and 3. So we have 1 by 3. Or if we turn it the other way, vertically it's 3 by 1. It's the same thing, according to the commutative law. Right? So 1 gives us a square, 2 gives us a rectangle, 3 gives us a rectangle. What about 4? So if we look at 4, we can arrange it as such, 1, 2, 3, 4. So it forms a long rectangle. That's fine, which is 1 by 4. And of course, we know that we could turn it the other and get it vertically as well. So 1 by 4. But we can also rearrange it 1, 2, 3, 4. So we get a different four-sided figure, which is now a square. So number 1 was able to rearrange to give us a different, could only give us a square. Number 2 was a rectangle. Number 3 was a rectangle. Number 4 was both a square and a rectangle. 2 different things. Number 5, if we arrange that, will be 1, 2, 3, 4, 5, which is a 1 by 5. And if we rearrange it vertically, it will be a 1 by 5. Can we rearrange this to get another type of rectangle? No. Can we get a square? No. Right? So 2, 3, and 5 only forms rectangles. Let's look at 6. For the case of 6, we can get 1, 2, running across horizontally. 1, 2, 3, 4, 5, 6. So we could get a rectangle. All of them can form a rectangle, which is 1 by 6. And we can rearrange it to form another quadrilateral. Well, let's see. 1, 2, 3, 4, 5, 6. So now what we can tell here, this gives us a rectangle. So 4, 2, 3, and 5 were only able to be arranged to form a rectangle, 1 wide by very long, but the others, 4 and 6, could be rearranged to form other shapes. As such, 1 is considered to be a square number. 2 would be considered to be a number which only gives us a shape which is 1 wide by however long, 1 by 2. So we call that P. 1 by 3 does the same thing, so we'll call that P as well. 1 by 4 gives us a couple different things. It gives us that thin long rectangle, 1 by 4, and it gives us another shape as well. So that gives us multiple shapes. The word for that is composite. The number 5 can only give us a long rectangle alone. So although just give us a thin long rectangle alone are considered to be a prime number. While look at number 6. Is it only a 1 by 6 we're getting? No, we can also rearrange to get another rectangle. So they have multiple rectangles. Another word for multiple is composite. So what we can tell here is that 2, 3, and 5 gives us 1 by something, 1 by 2, 1 by 3, 1 by 5, some sort of rectangle alone. So those are called prime numbers. 4 and 6 not only gives us those rectangles 1 by 4, 1 by 6, they can be rearranged to other quadrilaterals, rectangles or squares. So there are multiple things, as such they are composite numbers. 1 does not give us a rectangle, so it cannot be considered a prime number. 1 cannot form another shape, another four-sided figure, so it cannot be considered composite either. Let's go look at 7 now. And it'll give us a 1 by 7. Can it be rearranged to anything else? Let's think about it a little bit. Can we get a 2 by something with the 7 squares, or a 3 by something, 4 by something? No, we can't. Okay, let's try number 8. We can get a 1 by 8. Straight enough, all of them is going to give us that. Can it be rearranged for anything else? Well, we could get a 2 by 4. So we have a 2 by 4. That means it was able to not only form the rectangle, but form other shapes as well. Look at number 9. Number 9 will give us a 1 by 9. Can it be rearranged for anything else? We are thinking geometrically here, in terms of students being able to touch it or feel it concrete or draw it pictorially in order to understand the abstractness. So we're not going to be teaching that odd numbers or a prime number is one that is divisible by 1 in itself, right? It's so, but that is correct. But for students to understand that what do they see in their mind when they speak about a prime number? These words that form a definition, or they can see a shape. Right? And 9 can be rearranged as well. As such, we can see that it gives us a 3 by 3. Therefore, number 7 only gives us a thin long rectangle, a 1 by 7. So that would be considered a prime number. 1 by 8 gives us multiple things, so that's considered a composite. 1 by 9 gives us more than one thing, so it's also a composite. Let's do 10 to 12, and we could start with these. You can do the rest onwards. Try them yourselves and see whether it works as prime or not. 10 gives us 1 by 10, for sure. So therefore, 1 and 10 are considered to be the factors of 10. Can it be rearranged for anything else? Let's see. Can it be 2 by something? Yes, it could. It can be 2 by 5. As such, 1, 10, 2, and 5 are all factors of 10. And the number 10 can be rearranged to not just form a 1 by 10 rectangle, but something else as well. What about 11? Well, 11 gives us a 1 by 11. Can it be rearranged to a 2 by something, 3 by something, 4 by something, 5 by something, 6 by something? No. So we could only stay as a 1 by 11. And what about the number 12? Well, the number 12, we could get a 1 by 12. As such, 1 and 12 are factors of 12. Can it be rearranged to 2 by something? Yes, it can. It could give you a 2 by 6. And a 2 by 6 means the factors of 12 include 1, 12, 2, and 6. And when we talk about factors here, we're actually looking at the length and breadth. Right? So they can visually see what these things are when we talk about factors. Can we rearrange again? Yes, into 3 by 4. So we're able to show all the factors of 12. So let's consider 10 now. Does 10 only form a 1 by 10 rectangle? No, it forms something else as well. So therefore, it's a composite number. 11, does it only form a 1 by 11 rectangle or quadrilateral? That's all it does. So it's a prime number. 12 forms multiple things. So it's a composite number. Let's now go on. And we look at the ideas of if we introduce a block, one alone, then that's fine. What we can see here that if we're moving from left to right, we cannot travel across a level path. We have to go and jump down and then go across from left to right, right? So that is something that's weird. However, right, you see him, he has to go down and do that walking. So one is not really a level or even path. One is not even. But if we add a second one, what happens? We can see now, we can move, he can walk easily from one side to the other. So how many squares do we have there? We have 2 of them. So 2 is even. So we can shade that. Let's go again. If we add another one, then can we move from left to right, from one side, one wall to the other wall? Well, look at the pathway. So what happens to him? He has to go and come down, right? Jump down. So that is not even. So 3 is not even. What happens if we add another one? Well, can we move from left to right or right to left? Yes, he can easily move from one side straight across to the other side. So what does it say? 4 is, if we have 4 blocks, that is even. And we can represent that on the 100 chart. And of course, you can do the rest accordingly. Right? You can see for 6, it will be even, 8, 10, if you follow these things. And you can see this entire pattern that all of those are even. 2, 12, 14, and so forth. So 2 are even numbers, 4, 6, 8, 10, 12, 14. Going up the root doesn't just stop at 2 12s. So this is your 2 times table. And if we have our 2 times table there, look what we did. 2, 4, 6, 8, and so forth, right? And going up to 36. If we now considered forming groups of 4, not groups of 2 anymore, then we could ignore the 2, and let me remove it from the 100 chart. So we have 4. Can I form another group of 4? Here it is. Do I need the 6? No, 6 doesn't help me in groups of 4. So we can remove it from the 100 chart. So what that gave me, 8. If I form another group, then that gives me 12. I don't need the 10. And if I another group, don't need the 14 because it's 16. So let me remove it from the 100 chart, and I'm crossing it out from the left side as well. So you will find that most of your students, what they can at least do is 2 times table. But if they're doing the 2 times table, we are sure that within the 2 times table, look, there's another table in here. So another 4 will give us 20, not 18. Let's remove that. If we have another 4, do we need the 22? No, it gives us 20, and 4 is 24. So there it is. And then another 4 will be 28, 32, and 36. So what we see here is that every other one, if we look at the 100 chart, if you remove it, then we end up with, and we're continuing with this pattern, end up with the 4 times table. So remove the 62, 66, 70. So within the 2 times table, which most of the students know, there is the 4 times table. So there's no reason why this 2 times table, if you know it, you don't know your 4 times. You can write it out like on the left-hand side with the purple numbers there, and then cross out the other one and look 4, 8, 12, 16, and so forth. And you can see it on the 100 chart as well. That we removed half of the 2 times table and we left with the 4 times table. Right, so you want to do this with your students. You want them to take the 100 chart, shade out all the 2s, whether it's an even number, whether it's 2 times table, however you want to introduce it, forming groups of 2, and now we shift it to groups of 4, right? By repeating that there, so they have 200 charts. Both of them have 2 times table shade, and then the second one is 4 times, right? And of course, now if we have the 4 times, we can now, instead of forming groups of 4, we can form groups of 8. So we don't need the 4, so we can remove that from the 100 chart. And we could form another group of 8. So we don't need 12 anymore. And we're moving it from the 100 chart as well. And then if we forming another group of 8, so that's 2, 4, 6, 8, then that's not 20. That goes straight to 24. So we could remove 24 and go to 32 and so on and so forth. So we'll be taking each one of these from the 4 times table and we move every other one and we get our 8 times table. So if the child can write out the 2 times table, then they can get the 4 times table. And the 4 times table will give us the 8 times table. Right? So there's no reason why a child will not be able to come up with the answer for what the 8 times table is in an examination under their conditions. And of course, we can see also a pattern that we can, how do you go from 8 to 16? We could also go down 1 and move 2 to the left. Right? So look, we could continue that pattern here. 60, we move 68, we move in 76, we move in 84 and 92. So we have 80, 88, and 100. And we go down, so we add 10, 2 to the left, minus 2. Add 10, 2 to the left, minus 2. Add 10, 24 and 10, 34, minus 2 is 38. Add 10, 2 to the left, 41, and it goes back to what number? 40. So it holds. Now, if we do groups of 6, if the child knows 6 times table, then you don't need, that is within the 2 times table. So we can tell easily we form in 3 groups of 2. So we remove 2 and 4, and that will show us the 6. And we want to form another group of 6. A 2 would give us 8, another 2 would give us 10, but the third 2 would give us 12. So we could do that again and repeat the structure, showing you we move in 14 and 16, we have 18. Do it again, we move it again, 20 and 22, and we get 24. So hopefully you could see it there. We're moving 2 of them and leaving the third. We're moving 2 of them and leaving the third. Right? So if look where we are at 24. So if we were watching the 100 chart, then we could remove 26 and 28, and we're left with 30. You could see it on the columns, the table on the left side, or on the right side in the 100 chart. And we can continue like that. We move 32, we move 34, we didn't want it, we wanted 6 of them, 36. So we could remove 32 and 34 and we get 36. And following from here, we could remove 38 and 40, and we get 42. We move 44 and 46, and we get 48. We move 50 and 52, we get 54. We move the next 2, 60. We move the next 2, 66. Next 2, don't stop at it, just show them the pattern continues. Right? Because sometimes they give you 13 sixes. We move 80 and 82, we have 84. We move the next 2, we'll have 90. We move the next 2, 92 and 94, we have 96. We move this here, we'll have 102. That's what comes next. So look at the point that they're able to extrapolate that information to an abstract level where they're able to now tell what comes next, 102, without even seeing it on the tables. Because they're able to understand the pattern. And we come to the end here. So thank you very much. This completes our session on the operations of multiplication and division. And I wanted to also connect the ideas of odd and even, as well as factors and tables, which gives teachers a lot of problems in trying to figure out how to get the tables across to the students. All right, people, take care. Bye-bye.